All right, so next up we have Brice Gower from Augment Technologies. So Brice is the co-founder and CEO of Augment Technologies, an innovative technology company that specializes in artificial intelligence, IoT, and blockchain. He creates value for Augment's clients by developing solutions to complex high-value problems that, as non-AI specialists, they cannot solve by themselves. With 7 years of technical knowledge and experience utilized in a senior corporate role, his skill set lies in being able to produce robust and powerful computer systems and softwares to ensure commercial value is produced. Running a globally recognized team of AI specialists using Augment's lean and agile methodology ensures the team efficiently and effectively experiments with hypotheses to define whether an AI solution is viable or not, which saves time, energy, and wrongful investment for Augment's clients. So Brice is going to talk to us today about all movement policy, meta-reinforcement learning, heuristics, and a physics engine. Very interesting. Welcome, Brice.
Hello. That sounds good. Okay, thank you all for coming and listening to my talk. It's so good to be up on a presentation stage again. This is one of the luxuries that I really enjoy. So I'm hoping I can give you a really great technical presentation on machine learning-centric tools. I think I may be one of the more technical heavy talks here, but I think I was really grateful that Holly selected me to talk to you for that reason. With that, do I need to be pointing this at something? Technical difficulties. There we go. Thank you. There was a quick mention of legal departments, right? So this is my legal equivalent of "she'll be right, mate," and I'm just going to gloss over that and assume anyone who's interested reads that later. So I'm just going to quickly show you my agenda to fit within that tight 15-minute time frame, which is probably good because that's about as long as I can hold my gut in on camera. So I'm just going to quickly blast through an introduction and then go into a quick context of what data are we talking about and relevance to mining, and then an educational piece on me giving you a deep dive into reinforcement learning and some best practices, whilst then taking it even deeper to look at a novel technique that we've developed as a company that specializes in cutting-edge machine learning technology, and then wrapping up nice and quickly. So augment is a word that I've heard lots throughout this conference, which is really great given that we've got the branding all aimed exactly at augmenting. And we truly believe in this from the ground up. We want to empower people, make them have capabilities they couldn't before. And we look at this all through our vision, and we would never build 100% automation. We start with who is the expert, what are their skills, and how do we empower them? And it's set us on a great journey, especially dodging all these ethical issues and lots of other things that come up. By staying true to that ethic, we've just naturally walking a good path. Tamarin mentioned the lean age, and I really don't know what it was like without lean. I've lived lean my whole life, and this life cycle is exactly how we go through projects with customers. We religiously believe in bootstrapping. We don't pre-invest into any solution we presuppose the market needs. We work with customers and partners every step of the way, and we integrate the agile method in as well to make sure that we don't have this 3-year lag to deliver results to the industry. We get a minimum viable product out really, really quickly, and then incrementally to deliver more potentially shippable products as quickly as we can to produce value for our clients. And I really actually am excited about this conference because it's machine learning in mining. And we consciously chose to focus on the mining sector. Machine learning is going to change the whole world. We've heard about how it's absolutely letting the IT industry run away at a pace, and it's popping up all in oil and gas. But if you try to be everything to everyone, you become nothing to nobody. And by picking the mining industry, we've worked with so many amazing subject matter experts right through the whole value chain, where we've done some work in exploration, we've done some work in mine rehabilitation, we do a lot in operating space. And that all adds up to an overwhelming skill set for the whole team to understand mining. And I loved Eden's comment about the fact that mining engineers and all the specialists needs to learn the technology and work with it, where we're coming at it from the other angle, where we're technologists learning how to operate a mine. And you inspired me into a dangerous idea that I might buy a mine, because I think that we're thinking the complete disruptor legacy way. And then Matt from Adobe really scared the hell out of me with that legal comment, so I think I'll sit where I am sitting now. And I'm going to use the royal we, right? And I really want to emphasize that we are a team, and we work so well as a skunk works like small knit team. The skills are diverse, there's no duplicates, and we really actually pick up a lot of pieces where companies tried to do an ML project by hiring one poor graduate. It was their first task out of uni, and they don't have the support, right? You need a broad team of experts, and that's what we really bring to the table. There's been quite a few mentions of new technology into the mining industry is old, right? A lot of old technology is still not adopted in the mining industry. And Greg, our chairman, has a really interesting claim to fame where he still has an Apple Newton. He has an Apple Newton that he took thousands of meters underground in an underground mine and was logging claw, right? An Apple Newton. And so we hear all these companies doing remote or in the field core logging, and he sort of goes, how does the mining industry not have this down packed yet? And that's exactly the sort of adoption that we're going to try and fight. So with Augment introduced, I'd like to introduce the context of the data that we're working with. For anyone who works in open cut mines, hopefully blasting is something you're well familiar with, and particularly for the geologists in the room, what that does to your precious ore body. I'm glad the sound was off, because all you can hear in this is the siren just blaring. So this is a really nice video. This is a 4K footage from a drone that's sitting really, really high, because the fly rock sometimes can hit the drones anyway. And this is an example of the sort of imagery that we have to work with. This is the resource block model of what you just witnessed there. And the geologists in the room have mentioned all about how much effort they put into to make this precise, to make the uncertainty known and established. And so much effort is gone into this. And especially when you look at tools like Index's BlastDog around using the drill spacing opportunistically to increase the accuracy of this. And then the drill team come and do what the technical term is blow shit up. And that accuracy is then compromised. And so what every downstream application can do with that data is now not so clear. So particularly when we look at the loading, the immediate downstream application of what is waste, what is ore, where is my deleterious material, you need a very accurate map of how blasting moves your ore body. So why has this problem not been adequately solved to date? Again, the mining industry's been around, there's lots of technology. So from an answer of supervised machine learning, you cannot produce labels. To sample, to assay, the amount of data you need, it's impractical and very expensive. And the best practice to date has been what's called blast measurement instruments, so BMIs, which is where you put something in the in situ space and you just find wherever it landed. And so not only is there a question about whether that object moved representatively of the ore, but you also can only put things in so many places, inevitably around the surface on the free face. And you lose the resolution of what's actually happening. Marvel produces some amazing, relatively looking movies, right? Why can't we model this in a physics simulation and calculate it? And the mathematics of this requires too precise measurement of the initial conditions, which is broadly known as the three-body problem, right? To actually be able to simulate this properly, you cannot measure that accuracy practically. And lastly, you can see that hungry shovel in the background, right? That shovel is not going to wait for you to run a physics simulation. He's going to be in there scooping because the throughput in the mine will not be compromised. So these are all the issues of why this hasn't been practically solved. And to jump to the conclusion of what our solution is so that I can get deep into the data, this is a vector field produced by our reinforcement learning algorithm. We produce a unique three-dimensional vector of movement per cubic meter. And so what this does is it moves all the blocks into their final position. So our model has perfect conservation of mass, perfectly fits the muck pile and gives you this true 3D behavior where you can see that there's a big yellow region at the front where the most expansion was, if you recall from the video, and you can even see the turbulence in the power trough of where things have been thrown up and rolled back. And so this is our dynamic model that we've delivered, and the reason why it's so valuable is because rather than doing a mark out for the loading team on your in situ, on the left, right, you have this muck pile block model, which you can see how that beautiful pink vein that's going through, right on the corner free face, it is scattered, right? But that was right on the free face where the most chaos had. But rather towards the back, you can see it's just been shifted forward. And so there's so much to go through in this and analyze how the fluid dynamics of an ore body moves due to blasting. So with the problem introduced, I'm going to now cover some best practices of reinforcement learning. This is my educational piece to give you guys some deeper insight into some more modern machine learning techniques. So reinforcement learning is an interesting subset where most of you would be familiar with supervised learning, which is this idea of you have a label of what the answer is, and hopefully you guys haven't experimented with unsupervised learning because that's the black magic end of the spectrum. Reinforcement learning is explore and exploit. It's this idea of you have an unclear way of accomplishing your goal, but your goal is nonetheless clearly determined. And so this is a really interesting option when you can use cutting-edge simulations, you know the mathematics of the scenario, and you even have heuristics, right? Which is this idea of an expert system, knowledge that you can encapsulate in a limited capacity, right? And it leverages deep neural networks, which allow us to fill all of the graphics card memory and actually leverage more compute power than we could before talking to the physics simulation. But deep neural networks are incredibly nonlinear and multivariate. So when you're looking at blasting and you want to take into account the energy, the physics, the rock hardness, and even water and the probability of a charge failing, that can be accomplished in a model where linear extrapolation is just a very rough and inaccurate estimate. Chris from Curtin yesterday referenced the AlexNet achievement, which is in 2012, which is, again, one of these crowning innovations we like to point to. And so the CUDA compute library that NVIDIA released as a consequence, which you can use on any NVIDIA graphics card that is 2016 or later, is essentially this crowning innovation that we like to look at. And so that is what's leveraging high-performance compute power in a practical case that our mining industry can use. And lastly, I just want to emphasize with reinforcement learning, looking at that nice, simple diagram, is that it's not a PID controller. Although it's a closed-loop system, it's not linear. It is incredibly complex. And based on your training, you can intuit, and you can give it this idea of estimating where the physics engine is extremely explicit and does exactly what it says. So to give you an overview of our solution, to cover that architecture, Augment has built our own custom physics engine, which is the environment of that reinforcement learning system, where it acts, gets feedback on each action, and it actually empowers us to do a lot of amazing machine learning solutions because we have this simulation capacity. For this all-movement solution in particular, we've actually worked a lot with blasting experts, geologists, to create heuristics. So this is this expert knowledge that we've managed to encapsulate in software, and we use that in combination with measured variables and calculated variables as our system. And then lastly, to dive deeper past the simple reinforcement learning diagram, we use meta reinforcement learning, which is another closed loop above the reinforcement learning agent to optimize its hyperparameters. And we've done this in a unique way, which I'll enlarge for you now so that I can emphasize as part of my best practices talk. So rewards are the inner loop, which for our blast movement system is a quantification of how well one block has been moved into its final position. This is the standard process, that nice closed loop feedback where the agent then optimizes the reward to find the maximum reward. But we then have a very unique system where in training, we take checkpoints of the training process and we run that on blind validations. So these are data sets not included in the training set. And we then look at an evaluation score, which is similar to a reward system, but the evaluation is the completed blast. And so this is best looked at as a batch system versus a continuous system. So the evaluation systems score the batch, whereas the reward scores the individual notion. And you can see that allows us to have this really global optimization system that allows the agent to learn the physics and be able to intuit how a particular blast shape was created. And so to again touch on best practices, we have a large amount of heuristics, measured variables that we base each reward on. And so I'm going to walk you through a really interesting example in my niche technique coming up, where we split rewards out into individual quantified functions so that you can look at each heuristic as you go through and quantify its performance individually. But inevitably, you must rank which heuristic, which goal is most important. And so this is why we use scalars, the S values, to rank the priority of these. And this is where it starts to become a bit messy, is what is more important? How much more important is one aspect of the model than another? And this is where a really niche technique has been developed by us called random reward conditioning. So this is the deepest part of the technical talk for the people who are in the room interested in that cutting edge of machine learning. And we apply our lean and agile method here to work with all these sprints. So this was our hypothesis at the start of this sprint. If the reward scalars are added as an input variable to the policy, and the training process includes a function which randomly changes the scalars, will this condition the model to the full spectrum of priorities? So quantitatively, does this produce higher net eval scores from the model? And are we able to produce a better agent using this technique? So the experiment, as I mentioned, the state now includes the scalar values. So I've made that diagram slightly more complex by showing you where those state values come into the policy. And they are randomized. So at any different new start of a batch process, there's a complete random set of priorities. One thing that was low priority last time is now a high priority. And the point of including that in the state is that the agent understands this and can accommodate for the change in priorities. And this is all coming down to the fact that this reinforcement learning is based on an actor to critic system. So the critic is always trying to predict the reward it will get for the action it has chosen. And so this is this idea that actually making a bad move is good, so long as it predicted it was going to be a bad move. And we're now learning from bad situations, which is the exact same idea that Cortex posted about how the bad drilling practices will actually improve their model, right? And this is the mathematical process of how do you learn from a bad idea, which is by using this critic. So I'm now going to walk you through the experiment, right? This is the data science component of the talk. How did I mathematically go about experimenting with this? And so we have 6 reward functions. We chose the scalar value to be a maximum of 0.5 and a minimum of 0.1, discrete intervals of 0.1. And this results in 126 combinations of priorities that I could run for each individual blast. We then ran that on 9 validation blasts. Again, these are blind samples, so they were not included in training, which gives us over 1,100 output results to tabulate statistically to get a feel for how well this model runs. And so we've actually taken multiple checkpoints over a training run. So this is a lovely little tensor board plot, which no machine learning presentation should omit. And it shows that these different labels that I've tagged on the plot for you are roughly 24 hours apart. So because of the speed and the hardware we have, our agent runs through 126 blasts about every 17 minutes, which means between checkpoints, it's experienced 10,000 blasts that it's run through and learned from at different priorities. And so here is the evaluation function, which I've sanitized the names just to keep this high level, that I'm showing you, where each of the colors represents those 24 hours of training apart, so 10,000 blasts apart. And what you can see is happening here is actually that the mean, according to my hypothesis, has not really changed at all. But for this particular function, it's actually trending down, and the standard deviation is getting larger over the sample size. So this is just one heuristic. I've got this for all 8 heuristics that we're looking at. And you can see that the overall pattern is occurring where, again, the mean score is going down, right? Which is not what the hypothesis was. initially. So we're being surprised by these results. And again, here's the third heuristic, right, where it's the same pattern occurring again, where even more severely we're getting outliers and the minimum score is going up with more training. So this is a net mean average of the 8 heuristics that evaluate it, and the overall pattern is that these minimum and maximums increase with the more training. And so what this is actually showing you is that at the start, the agent doesn't understand bad sets of priorities. And as you give it more experience of diverse ranges of priorities, it's actually better able to predict what a bad move is. And so when you ask it to produce an odd set of priorities, you get the low score. And this is basically coming to our conclusion here, is the idea that you can see that the actual range of priorities were conditioned properly into the model, which was the experiment of what we wanted to accomplish. And we can cherry pick that peak maximum up there. We don't actually want to deploy that range of capability. We want to deploy the most consistent, highest level performing agent, which I cherry picked that parameter combination up there from. And what this does is it means that our agent knows what a bad move is, but understands the optimum priorities for achieving the best move. So if I could leave you with one summary, it's this idea that reinforcement learning is about exploring and exploiting. You must properly understand the environment, and you need to be able to predict what a bad move is, as well as understand what a good reward is. And above all else, by using the lean method, you can rapidly iterate over hypotheses like this, right? My hypothesis was actually disproved to be false, but because the outcome was clear, the lessons learnt were clear, and we still produced a really good result within a really short time frame. That's my deep dive into reinforcement learning, going through a very niche technique. But I do want to leave you with the fact that now that we have this great model that estimates how blasting moves the ore, we're actually unlocking a really interesting set of value propositions downstream, where we track that geology through the load and haul teams and can now attempt to model the stockpiles, as well as going back upstream, where we're actually able to predict the muck pile in its spatial location and its topography from the blast pattern and the in-situ geology. And these will actually evolve into further up and downstream tools. As our mining clients adopt this, we get in more data and we grow as a company. Interoperability is becoming a common theme around here. So one of the biggest commercial problems we had to solve was the silos between the data. So because we take data from the blasting department, the geology department, and the survey department, there was actually a lot of effort in change management just to get those parties to play together, and actually also the consistency, right? Because this is a critical operations solution. It needs to be 100% reliable and as quickly computed as possible. So what we found is that whilst we were able to manage this for our pilot trials and getting off the ground, where we really see a huge opportunity for interoperability is in the blockchain space. And we're working on a product for this exactly, where the idea is that the blockchain ledger stores all of the measured variables of operation privately. So a mining company has it all privately stored for their own auditing purposes, and they know that it's incorruptible and decentralized. However, due to layer 2 functions and exploring options like zero-knowledge proofs, you can actually offer that information to regulatory bodies, consultants, and even other mining companies with the exact control needed to know what you can release, whether you can release it or not, and actually using zero-knowledge proofs show that they used it without even letting them see the data at all. So that's again why Augment Technologies covers that broad spectrum, because the machine learning processes are driving that solution. Does the model help predict or account for blasting issues such as frozen shots, uninitiated lines, or tow? Yes. So one example that's actually really good at is deflagration. So deflagration is a scenario where water gets into the charge and it doesn't detonate properly. You get this big orange smoke scene, and it's very clear from a video point of view. So because we rely on surveys of the muck pile, and then our algorithm moves the in situ blocks to perfectly fit that post-blast survey, the algorithm has got a really good intuition for where these shots have failed because of the fact that if the shot had detonated, additional energy would have been imparted and you would have seen more movement. So this is part of a conservation of energy function. When you look at mass versus kinetic energy, as long as you've got a model for kinetic friction, you can actually do a lot of interpolation. And so our model is particularly good at providing feedback, and this is what our muck pile prediction routine software is going to be particularly powerful on, because you could actually, in a simulated environment, turn one charge off or on and see the resulting change in the predicted muck pile shape and location. Yes, we did encounter overfitting in the feedback loop. Overfitting is actually a bit of a dirty word, right? And so if you are not conscious of bias in your data set and you unintentionally produce an overfit model, you can get into a lot of trouble. However, overfitting is a really, really powerful way to prove that your system works in isolation. If you're consciously setting up a system of saying, can we actually predict a really good move for just one blast? That's an important hypothesis to explore and actually validate, right? Because then the subsequent hypothesis is, well, can we generalize this, right? Can we now do it over a greater range of examples? And you don't want to skip that step of in isolation. So overfitting is something that's important as long as it's done consciously.